Recording transcribing.
Let me check. James?
Yeah. Okay, guys, we're gonna get started. Okay, so I just wanted to say before we start real quick, if any of you are going to be fasting on Friday, I recommend bringing a small snack and maybe like a water bottle, because Dr. Bean does give you guys like a 5-minute break once you guys can break your fast to eat that snack. And she gives that time back to you, so don't worry about like not having the time. Just something to keep in mind. But anyways, this is the spring 2022 exam. And so we're just going to jump right into it. We're going to get started with our nomenclature. What? Okay. And again, if you can't hear me, you need me to speak up or like adjust the mic at any time, please just raise your hand. All right, so getting started with the nomenclature. So we've got our benzenes, and in this chapter, we've introduced our like ketones and our aldehydes. In addition to everything else that we've learned previously, that's going to be fair game. But real quick, for our priority for nomenclature, aldehyde is going to be higher priority than ketone, which is going to be higher priority than alcohol. So just remember to keep that in mind when you're looking for your parent chains. And then these are some benzene common names that you should definitely know going into the exam. These can show up and become the parent chain, as we'll see in this first question. So it's very helpful to know these to make it a little bit easier on yourself for nomenclature. What's up, James? I didn't put aniline on here because we haven't gone into amines yet. So I don't think that she would put it on the exam. Okay. So again, amines is going to be the next exam, but this would be aniline, which is the benzene with just an amine group on there. But I would probably just look at these ones because we haven't gotten into amines yet. All right. So when we look at this first question, the reason why I brought up all those common names is because if we look over here to the right, we have this carbonyl with this CH3 group over here on the right. And so including that into our benzene, that is actually going to be acetophenone, which is one of our common names. And so that is going to be our parent chain. And so that can make it just a little bit easier on you naming. So you had that parent name, that common name. So that's kind of like one less substituent that you have to worry about naming. So that's going to be our parent name in this case. And then we just have to worry about our subs. So other than the group on the right, we have this group over here on the left. And so again, starting from the parent, we're just going to go and number around the benzene. So 1, 2, 3, 4. And if you go the other way, you'll still get the same nomenclature, or sorry, same numbering. So in this case, it doesn't matter which way you number the ring. And then when we number our substituents that come off of our parent name, we have to start at the carbon that is connected to the parent. So we're going to start numbering from the right here. So we've got 1, 2, 3, 4, 5. So this is going to be a pentyl group. And you'll notice that we have a ketone at carbon 4 on that pentyl. And when ketones are our substituents, they're going to be called oxo. And so since this is a complex substituent, we're going to put that substituent on our substituent, and we're just going to throw that all in parentheses. So pentyl is going to come from the 5-carbon chain, and then at carbon 4, we have that ketone, which is going to be where we get that oxo. And there's no other substituents on that benzene ring, so we can just throw that over here. And the number that it's on the benzene ring is carbon 4. So the complex substituent name is going to be 4-4 4-oxopentyl. Again, we don't have any other substituents. In this case, we don't have any stereochemistry. There's no wedges or dashes. You don't do the E and Z for the benzene ring, and there's no other double bonds. So in this case, we're good to go on stereochemistry. So we just have to throw this one together. So we've got 4-4-oxopentyl, and then acetophenone. All right, any questions on that one? Pretty easy, pretty easy. Okay. Moving on to the second question, we've got a couple of benzene rings and we've got an aldehyde right here. And so remember, going back to our priority, aldehyde is going to win. So we're going to start numbering from this aldehyde carbon. So this is going to be 1, 2, and we want to get the longest chain possible. We could go to the left and get 3. That would be less than going to the right. So we got 1, 2, 3, 4, 5. And the benzenes are going to be substituents. So you're not going to start numbering onto the benzene ring. You're going to treat the whole benzene ring as a substituent. So for our parent name, we have a 5-carbon ring. So that is going to be pent for that, what is called the root of the word. And then we have our aldehyde. And so aldehydes are going to get the ending Al. So we have pentan and then Al for the aldehyde ending. In this case, unlike ketones, you don't have to put the number of where the aldehyde is because it's always going to be on carbon 1. It's always at the end of a carbon chain. So we have our parent, which is going to be pentanal. And then we just have to worry about these substituents that we got on here. The only substituents we have are these benzene rings. There's no other substituents. But what you'll notice is that one of them has an additional carbon attached to it, whereas the other one is just directly connected to the parent chain. So this is also kind of similar to the common names I would recommend you guys know. So whenever we have benzene as a substituent, we have 2 options. So if it has this extra carbon group, and then it's connected to the ring, this is going to be benzyl. Or we could have the benzene directly attached to the ring, and that's going to be phenyl. So these look very similar. Definitely do a lot of practice with these two because it is very important to know, very important distinction to make. But those are going to be the substituent names for a benzene substituent. So in this case on the left, since this benzene ring has an additional carbon here, this one is going to be benzyl. And that's coming off of the second carbon on that chain. So it's going to be 2-benzyl. And then on the right, this one is just directly connected to the parent chain. So this one's just going to be phenyl. And that's coming off of carbon number 5. So again, we've got benzyl and phenyl. And so those are our substituents. And again, we don't have any stereochemistry for this one. No wedges, dashes, no other double bonds. So we're good to go. We just got to throw this all together. So we're going to throw these substituents on by alphabetical order. So we've got 2-benzyl, 5-phenyl, and then our parent, which is pent and al. All right. Any questions for this one? All right, let's move on. Okay, so this one is a little bit more complex. We've got some multiple functional groups in here. So we have an alcohol here, we have a ketone here, and we have an alkene here. And so again, just remember, ketones are going to be higher priority than alcohols. So we're going to have our parent name be based on the ketone. And so that's going to be the ONE ending, the own ending. So this ketone's kind of in the middle, so I'm just going to start numbering from the left and see what we get. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then numbering from the right. 6, 7, 8, 9. Okay, and so then when we compare these two, we can look at the substituents, which are now going to be the alkene and then the alcohol, or the non-parent, I should say. And so with the orange numbering, the alkene here starts on 1, and the alcohol starts on 7. So we've got 1 and 7 for our numbers. In the light blue, starting from the left, we get 3 and we get 8 as the numbers that we'd put. So in this case, we're going to be going with orange because that gives us the lower numbers for those non-parent structures. And then either way we number it, we get 9 carbons for the parent. So that's just going to be the non root. And then remember, we have to do the alkene. And so the alkene starts on carbon 1. So we've got non-1-ene. And then the -one ending goes at the end. Again, you do have to indicate the number for the ketone because it could be anywhere on the molecule. And so in this case, we have it at carbon 5. So we'll put 5-one. So our parent is going to be non-1-ene 5-one, or you could do 1 non-ene 5-one. Either one would be fine. So that's our parent. Then we just have to worry about this alcohol as a substituent. And so remember, alcohols, when they are not the parent, their substituent name is going to be hydroxy. And so it starts on carbon 7. So this is going to be 7-hydroxy. We don't have any other substituents on here. For stereochemistry, we don't have to worry about stereochemistry for the double bond because over here on the right, they're both hydrogens. And when you have two of the same group on the same side, you don't have to worry about stereochemistry because you wouldn't be able to distinguish between them. So we don't have to worry about it for the double bond, but we will have to worry about it for this alcohol over here. And so with our wedges and dashes, since this is a chiral carbon, we're going to do our RNS nomenclature. So remember, the highest priority gets the number 1, lowest priority is going to get number 4. And then going to the left, and to the right, actually, we have the same group here. These are both CH2s. So we're just going to move on to the next carbon. On the left, we have a CH3. On the right, we have this carbon that's connected to the ketone. So the higher priority is going to be on the right. So that's going to be 2. Going to the left is going to be 3. Excuse me. And so when we get our numbers, I'm just going to move them out here. We get S for our nomenclature. And the lowest substituent is, or the lowest molecule is on the dash, so we don't have to worry about flipping it. So it's just going to be S. And that's all the stereochemistry. And so we just need to throw it together. So we've got S, and then our substituent, 7-hydroxy, and then our parent name. So non-1-ene 5-one. All right. Any questions? That's a great question. I always just say there are some times when you can leave it out. Like for example, for the RNS, since we only have one here, we can leave the number out for that. I always recommend just putting the number anyways, because that just builds your habit of putting in the number. And if it's not needed, you won't get points off. But on the other hand, if you didn't put it and you did need it, you would get points off. So I always say just try to put the number there. And I was a bad example because I didn't do that for my RNS. But so for that, for the RNS on this one, you could do, it would be 7. Yeah, and so that's kind of the question that she just asked. If you didn't have to put it, would you still want to put it? I just say go for it, because again, if you put the number there and you don't need it, you're fine. But if you don't put it and you do need it, then you'll get points off. So it just builds a good habit. So, okay, we're going to move on to the facts section. And for the facts, definitely know your aromaticity. And I know this is probably going to be the hardest, maybe most tedious part of the facts section for this exam, but definitely do some practice with it because it is going to be very important. Lots of these molecules can kind of look like one thing, or they might look like one thing initially, but when you do resonance with it, it'll be something different. Okay. And so these are just some rules about aromaticity. So you've got your Huckel rule, which is going to be the 4n plus 2, or you could do the 4n for aromatic. I say just pick one and go with it. You don't have to use both. Just make sure that when you do your equation, you want to get an integer value for the equation that you're using. So if you're looking for aromaticity and you're using 4n plus 2, you want n to be an integer for that molecule to be aromatic. And so going back to like, I don't know, 5th grade math or something, integers are going to be whole numbers. So you don't want decimals or fractions. So you want like 0, 1, 2, 3. You don't want like 1/2 or 3/2 or 5/2. And then again, the same for the 4n rule, just depending on which one you want to use. If you want to look for anti-aromaticity, you'd look for 4n with n being a integer, but it'd be the same thing either way. You can just pick one and stick to it. And so our aromatic compounds are going to be the most stable. Our non-aromatic is kind of in the middle, and then anti-aromatic is going to be the least stable. And so we don't have a formula for the non-aromatic. Non-aromatic will just be when it doesn't satisfy those aromatic rules. So if it's non-cyclic, so if it's just like a linear structure, if it's non-planar, so if it's an sp3 atom, so maybe something like this, where you've got 1, 2, 3, 4 regions, so that would be sp3. And then determining between aromatic, non-aromatic, and anti-aromatic. If a structure can be 2, or usually it's just 1 or 2. For example, if you're looking at a structure that can be aromatic and non-aromatic, you're going to choose the one that gives you the most stability. So if a molecule that we're looking at is going to be aromatic or non-aromatic, we'd go with aromatic because that's more stable. And we can get into the actual questions so we can kind of see that better. All right, so starting with this first one on the left, we don't have any oxygens or nitrogens, so this one's kind of easy. We're just going to count the double bonds that we have. So we've got 2, 4, 6, 8, 10, 12 electrons. And there's no resonance that we can do with this one. These double bonds are kind of just locked in place. So for this one, 12 is going to be, it would satisfy the 4n rule, and it would not satisfy the 4n plus 2. So this one is going to be anti-aromatic. Sounds a little bit easy, but they will definitely be tricky. Okay. So going into the second structure, we have a lot of lone pairs here. So right now, if you'll notice, you see this oxygen has 4 regions. So that's going to be an sp3 oxygen. So we might say it's non-aromatic at first, but again, always look at the resonance because it might be something different. So if I wanted to do some resonance with this one, I could potentially push one of these lone pairs up and then push this double bond back onto that oxygen. And then so our new resonance structure would look like this. Sorry, a little bit not that great, but it's okay. Okay, so this would be our new resonance structure. So this oxygen up here now is negative. The one at the bottom is positive. And so now when we look at this oxygen right here, we see that it has 1, 2, 3 regions. So this one is now going to be sp2. So it could potentially, I apologize, it could potentially satisfy the aromatic rules. We'll just have to keep looking at the structure. All right. We also have this carbanion up here at the top that we need to look at. So we could push this carbanion towards that oxygen. And in this resonance structure, all right, so that'd be our new resonance structure. Again, this carbanion went from being sp3, and now it is going to be sp2. You've got a hydrogen there that you got to watch out for. So we've got 1, 2, 3 regions. So this one is sp2. So this one could satisfy the aromatic rules. So now we just have to look and see how many pi electrons we have in this aromatic, or sorry, in this cyclic structure to see if we have aromaticity. So starting, I'm just going to look at the one at the top that we just looked at. So we have 2 from this double bond. We have 2 from this double bond here, and we have 2 from one of these lone pairs on this oxygen. So this would give us 6 pi electrons, and 6 satisfies the aromatic rule. So this one could be aromatic. But just to double check, let's look at the one that we did on the bottom. We have 2 from this double bond. We have 2 from this double bond, and then we have 2 from this carbanion. So this one also gives us 6. So this one could be aromatic. And so again, since the oxygen and the carbanion can perform resonance to become sp2, this one will actually satisfy the aromatic rule, and so this one is going to be aromatic. Any questions on that one? Mm-hmm. Up here? Yeah, so it is sp3, but since it's not in the ring structure, it wouldn't be contributing to the aromaticity or non-aromaticity. It's only whenever it's within the ring structure. Yeah, that's a good question. Mm-hmm. Right here? I'm sorry, could you repeat that? Oh yeah, we could look at it that way. So we're looking at it here. We've got two from the double bond, and then we've got 2 from the carbanion, so it'd also be 6. And then one other thing real quick, the short way, I remembered it when I was studying. Whenever you have atoms that look like they could give more than 2 pi electrons, just remember that an atom can only give 2 pi electrons to aromaticity. So even though these oxygens have, down here at the bottom left, even though these oxygens have 2 lone pairs, they can only contribute 2 pi electrons total. So that's why we're not saying that they donate 4, we're saying that they just donate 2. And so those structures give us 6 pi electrons, and so we're going to say that one's aromatic. Okay. Moving on to the third. All right, so we have a sp3 nitrogen here. We've got an sp3 nitrogen. It's got a lone pair. It's got 3 single bonds. So that's going to be sp3. Looking at the pi electrons in this structure right now, we've got 2, 4, 6, 8. And so 8 would give us non-aromatic, or sorry, anti-aromatic. And if we do the resonance, we can make the nitrogen become sp2. So let's see. So in this resonance structure up here, this nitrogen is now sp2 because it's just got the 3 bonding regions. However, even in this structure, when we look at our pi electrons, we've got 2, 4, 6, 8. And so again, 8 is going to give us anti-aromatic. And so because we're looking at anti-aromatic versus non-aromatic for this structure down here on the left, the first structure, we're going to go with non-aromatic because non-aromatic is more stable than anti-aromatic. The only time that you're going to do anti-aromatic is when a structure is kind of forced to be in that state, kind of like this first one we have here where it can't perform any resonance to change. So, okay. All right, for this last one, this is another little thing that you should probably remember. For boron, boron is weird, and it is fine just having 6 electrons, so 3 bonds. So even though it's got all single bonds, it's actually going to be an sp2 atom because it's got 3 regions and it's satisfied just having 6 electrons. So in this one, we can't really do any resonance with this boron. We're just going to have to count our electrons. 2, 4, 6, 8. All right. And so we've got 8 pi electrons. And again, we can't really do any resonance with this one. Can't really push anything around. So this one is just going to have to stay as anti-aromatic. All right. Any questions for aromaticity? Yes. Yes. So in the first structure that we're given, the nitrogen is going to be sp3 because it's got those 4 regions. It's got the lone pair and the 3 single bonds around it. And when we look at the amount of pi electrons in the cycle, it gives us 8 pi electrons, which would be an anti-aromatic structure. But since this nitrogen can be sp3, the molecule is going to want to stay sp3 and in that non-aromatic form because non-aromatic is more stable than anti-aromatic. So it's not going to want to shift to be anti-aromatic because it's just not stable. Okay. Any more questions on aromaticity? All right. This is also a pretty common question that you might see. You have a rate reaction question for CH3Cl and AlCl3. So unfortunately, you will have to kind of know your reactions for the facts section too. But I always like to remember the AlCl3 as the catalyst, and that one's going to be either your Friedel-Crafts acylation or alkylation, depending on what this one is. But this one's going to be Friedel-Crafts. And so you remember for Friedel-Crafts, you need to have electrophilic aromatic substitution. And so for EAS, you want donating groups. And withdrawing groups are going to decrease the rate. So you don't want withdrawing groups. All right. And then another thing to keep in mind, it's less important, but steric factors can also, steric hindrance can also decrease the rate of EAS. It's less important than the withdrawing thing, but it is a factor that you will need to consider. So looking at these structures, looking at what the benzene ring is attached to, we have, it looks like this dimethyl. We have a nitrogen amine, and then we have a nitrogen, but specifically connected to a carbonyl carbon. And so in the middle, this is going to be just a regular amine group with the nitrogen by itself. Whereas over here on the right, we have what's called an amide. And so amides are going to be, in this case, this one's going to be donating because the electron flow is going to be flowing towards that nitrogen and towards the ring. For amines, you'll definitely have to watch out for this if you get a Friedel-Crafts question. Amines are going to like absolutely ruin this reaction because the amine is super basic, and instead of attacking normally with the molecule that you want it to react with, it's going to attack the catalyst instead, and you won't get hardly any of the reaction that you actually want. So anytime you see an amine, just nitrogen just by itself with Friedel-Crafts, it's going to ruin your reaction. So this one's going to give us the lowest rate. And then between the left and the right, we just have to compare the donating factors. So over here on the left, we have a couple of methyls. And so these are going to be donating, but they're only going to be donating by induction. There's no resonance or anything that's going on. Whereas over here on the right, this amide is going to be donating by resonance. And so we had a lot of practice with this last test. So donating by resonance is going to be a lot stronger donation. So this structure on the right is actually going to be our fastest rate, whereas this one over here on the left is going to be in the middle. All right, any questions on that one? Okay. Okay, we have another reactivity question. We got nucleophilic addition reaction. And so for NAS, you'll want to remember that you have your nucleophile. And so with a nucleophile, you need to have a either fully positive or a strongly partially positive atom that the nucleophile can attack. Because you've got this electron density that's going to be attacking the kind of lack of electron density. So in this question, we're going to be looking at the partial positivity of the atom. And so here, our potential atom is going to be this carbonyl carbon, because that oxygen is going to be pulling a lot of that electron density and making that carbon partially positive. And so between these, we have a couple aldehydes and we have a ketone. And then we have kind of slightly different substituents on the right. So just remember that aldehydes are going to be more partially positive than ketones. And that is because they only have one group on one side that can donate some electron density. The other side is just a hydrogen, and that can't really donate any electron density at all. So aldehydes are going to be more partially positive than ketones. And so since we have two aldehydes versus one ketone, this ketone, unfortunately, is going to be the least reactive. And now comparing the left and the middle, we have two aldehydes. The only difference is their substituents. So we've got a dimethyl and we've got a single methyl, monomethyl. And so with this one as well, you'll want to watch out for steric hindrance. Or you could just think of it as the more groups that a atom or molecule has, the more it can donate to that partially positive. So the left structure can donate more electron density to that partially positive carbon than the middle structure. So this one is going to be, the middle is going to be more partially positive and therefore more reactive. So this one's going to be the most reactive, and this one is going to be the middle. All right, any questions on that one? Mm-hmm. Yeah, so steric hindrance can affect it, but again, another way that you can just think of it is since the left structure has two methyl groups, it has those two methyl groups that can donate some of that electron density towards that partially positive carbon, whereas the middle structure only has one group to donate, so it won't be able to donate as much, so it'll be more partially positive. It's kind of like a backwards thinking, but yeah. Mm-hmm. No problem. Yes. Halides are actually going to be withdrawing. So they're withdrawing, but when we get to the reactions, they're going to be ortho-para-directing. It's kind of weird. They're like the weird exception, but they are withdrawing. So if you were looking at like the amine versus the halide, then the halide would react more because the amine is just attacking the catalyst in this case. if you were comparing like just maybe like a carboxylic acid versus a halide, I would think that the halide would be more reactive because it's withdrawing by induction, whereas the carboxylic acid would be withdrawing by resonance, so it'd be a stronger withdrawer. So does that answer your question? I can like yeah, I would still think yeah, so it would still react. It would just react less quickly or it'd have a slower rate than maybe the left and the right here. The amine is kind of like the weird one where it just attacks the catalyst. So the amine is going to be one to watch out for just because it does something completely different. But yeah, if this was just like a halide, something like this, yeah, it would still react. It just wouldn't have as fast of a rate as the other ones that were given. The amine one is just like not going to react at all. So it's like the worst of the worst. So yeah. All right. Any other questions on any of the facts questions we've gone over so far? Okay. All right. This one's a little bit strange. We've got carbonyl stretch in the IR spectra. Kind of don't want to see the IR in the facts questions, but it is what it is. For these frequency questions, you'll want to remember that conjugation lowers frequency. And then another thing that lowers frequency is more alkyl groups. So like if you have a more substituted carbon, that would also lower the frequency. And then in this case, we have different size ring structures. So we have a pentane, cyclopentane, we have a cyclopentane, and we have a cyclobutane. And so ring strain is going to increase the frequency by a lot. So just keep those in mind. And so when we look at these structures, we've got two cyclopentanes versus a cyclobutane. And so again, since the cyclobutane is a smaller ring, it's got more ring strain. So this one is going to be the highest frequency. So we're going to say that one's number 3. And then comparing the left and the middle, the only difference is the conjugation of these two. So when we look at the double bonds, we can see that on the left, the double bond and the carbonyl double bond are conjugated, which is just like alternating between double, single, double. Whereas in the middle, they're too far apart. We have the double bond and then we have single, single, double. So this one is not conjugated. Whereas the one on the left is conjugated. And so conjugation lowers frequency. So the one on the left is going to be the lowest frequency. The one in the middle is going to be in the middle. Any questions on that one? All right. Okay, we have a free response question. Hate to see it. I'm not sure if she's going to put a free response question on the exam. Usually it's just like a short, like couple sentences, not even. Bullet points is fine. But I have seen from the previous exams that there's usually a free response question on the second exam. So yeah, you hate to see it, but so we're given this structure and we're supposed to explain why the structure has a large dipole moment. So one thing to think about if you get a short answer and you just have absolutely no idea what to do, try to just think back about the most important questions and kind of topics that you've gone over for the chapters. So in this case, the big thing is aromaticity. We're talking about benzene, we're talking about aromaticity. So if anything, just put down like the keyword that you've been talking about and that might get you a couple points. So don't give up hope if you see a free response and you just have no idea what to do. But going into this one, we can do some resonance with this one, just throw around these double bonds. And so if we throw this double bond here to the left and we do our resonance, all right, so we're just throwing that double bond and kind of isolating it on that carbon on the left. And so now when we look at this structure, kind of crazy. We got 2, 4, and now we've got 6 electrons on that ring. And if you remember, 6 electrons gives us aromaticity. And if we look over here on the right, we have 2 electrons. And this one's kind of strange, but if you do the Huckel rule and you solve for n, that is still an integer. So this one is also aromatic. And so, again, what we know about aromaticity is it increases the stability of a structure. And so because in this resonance structure that we have 2 aromatic rings, the resonance is going to shift quite heavily towards this resonance structure. And so this is going to induce a dipole moment because we have this charge here on the left. So for this one, we drew our structure, and then for our reason, this is going to have an unusually large dipole moment because the resonance structure is aromatic, which is very stable, or very stable. And the structure has a dipole moment. And that's where the structure has a charge, and that's where the dipole moment is coming from. So again, this one's just it's a very brief response. There's usually a couple things that she's wanting you to look at. So in this case, the kind of keywords are going to be aromaticity, and then you have the charge, which gives you that dipole. So it doesn't have to be like a whole essay. You probably won't have a ton of time for each question, so she's not expecting you to write like 5 sentences. And if anything, come back to it at the very end if you're really having trouble with it. But just keep in mind the key topics that you've looked at, and kind of just think of the key points that she might be asking you to look at. Any questions on this one? Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. So if we do Huckel's rule for this one, you'll get n equals 1. For the sake of time, though. I just wanted to show it on the one on the right specifically because it looks a little strange just being a cyclopropane and then with 1 double bond, but it actually is aromatic, which is kind of funky. But hey, any other questions on that one? Yeah. All right. It's more of they're 2 different things that kind of just join together to have this perfect, beautiful aromatic resonance baby. Yeah. Mm-hmm. Yeah. No, in this case, it just happens to be that it has a dipole moment with its aromaticity, because when we do the resonance, it creates a charge, and then the aromaticity just kind of keeps it in that charged state, because of the stability. Did you have a question? Yeah. Hmm. Yeah. Yeah. Well, the dipole moment comes from the charge. So the reason why this one has the dipole moment and the reason why we're factoring in the aromaticity is just because when we form that resonance structure, it forms a charge, and then the aromaticity just kind of keeps it in that structure. So if it was like, if we formed a benzene from the resonance, that wouldn't have a dipole moment because there wouldn't be a charge. But in this case, it just kind of happens that there is a charge, and that contributes, or the aromaticity makes it stay in that structure, which contributes to the dipole moment. So if this one wasn't, for example, if this one wasn't aromatic and it had a charge, the aromaticity wouldn't contribute to the dipole moment because it's not keeping it in that structure. Yeah. hmm Yeah, if it was just non-aromatic and it had a charge, it would just be like a regular resonance structure. But since this one is aromatic, it kind of keeps it in that state longer, that charged state longer. So it's kind of more charged than like a normal structure would be, if that makes sense. Yeah, it's kind of a weird way of thinking about it, but yeah. Okay, we're gonna move on to the link page. We're gonna move on to the reaction section. So again, definitely know those the first page of your aromatic reactions, and then EAS, NAS, and those should be the big ones. And then just make sure you're refreshed on all your previous reactions. But for this one, we've got HNO3, H2SO4. So this one is going to add a nitro group. And so we're going to want to add that nitro group to the most activated ring. So the ring over here on the left has a nitro group already on it. And so nitro group is going to be deactivating. So we're not going to add our new group onto the ring on the left because it's deactivated. It doesn't want anything else on it. But this OCH3, on the other hand, this one's going to be a donating group. Oh yeah, and this one's one of the EAS reactions. So that's why we want donating groups. So the donating group is going to increase the activation of that ring. So we're going to add the nitro group over on the right. And then you'll just have to keep in mind your ortho meta para rules. So donating groups are going to be ortho and para. And then withdrawing groups are going to be meta, with the exception of halides, which are going to be orthopara. But in this case, we just have an OCH3. It's orthopara directing. And so we can either add our group here, here, or here. Never put a group in the middle of two other groups. That's just going to be too hindered for it to react. So we're not going to put our group in that position. And then we kind of have two options. We can put it either para next to the big benzene ring, or we can put it ortho to the OCH3. And in this case, I'm just going to put it ortho because it's a little bit less hindered. So it'd probably be more likely to form in that position. All right. And then we've got NaNH3 and methanol. And so this one is going to be our Birch reduction. And so Birch reduction is a little bit funny. It turns a benzene into a cyclodiene. And so keep in mind that we want our withdrawing groups. They are going to go to sp3. So we're going to take our withdrawing groups, and then they're going to end up on a sp3 carbon. So when we do this reduction, we have two withdrawing groups. We have those nitro groups that we have. And so I would say just draw the structure first and then worry about the double bonds last. So we've got OCH3, we've got NO2, got NO2. And so now we're going to worry about where our double bonds go. So we want our withdrawing groups to end up on an sp3 carbon. So I'm just going to put our double bonds here. That puts the nitro group on the left on an sp3. Over on the right, again, we want our nitro group to be on an sp3. So I'm going to put our double bonds here. And we are good to go. And this could be a product of that reaction. Any questions on that one? Mm-hmm. Yeah. It's mostly because of steric hindrance. So the benzene it would technically be a donated group, so it would be orthopara. But since that would just be by induction, there's no resonance going on there. This OCH3 would be donating by resonance, so it'd be the stronger one. So you'd go with that one. But then, yeah, so the reason why I didn't put it in that position was just because it would be pretty hindered with that big benzene ring right next to it. So I just put it next to the OCH3, which is a little bit smaller. Okay, going on to the second reaction. All right, so we've got a sulfur here. Anytime you see a sulfur like this, just kind of think of it as an oxygen. They're in the same, what is it, period or group? They're in the same column, so they're going to react pretty similarly. So don't get too intimidated if you see like a sulfur. But anyways, we've got our acyl chloride, and we've got our AlCl3. So this one is going to be our acylation. And so we're just going to add on, we're going to form a ketone with that one. And so this sulfur group, this one's going to be, again, kind of acting like an oxygen. So this one is going to be a donating group by induction. Not that it matters, it's the only group on there. But this one's going to be orthopara. And so in this case, I'm just going to throw it in the para position because that's like the absolutely least hindered. You could probably put it right next to the substituent, but I'm just going to put it off by itself. It's going to like it better. Okay, so that's 1, 2, 3. Okay. Okay, so that's a product of step 1. All right, step 2. This is going to be what's called the Clemmensen reduction. And so this one's kind of funny. It takes ketones and it turns them all the way back into the alkyl. So most of the other reducing agents we've seen so far turn a ketone into like an alcohol or something, but this one's actually just going to take it all the way to the alkyl and get rid of that oxygen. So it basically turns a ketone into just a regular alkyl group. So that's going to be the product of that reaction. All right. Then for step 3, we've got Br2 FeBr3. This is another EAS. We're adding a bromine onto our ring. And so we have 2 donating groups here. We have an alkyl, and then we have a, I can't even remember what it's called, but it's the sulfur group. Again, this one kind of acts like oxygen. So this one, like we said earlier, is going to be donating by induction. The group on the bottom is going to be donating, sorry, by resonance. Wow, I should have caught that. Resonance, donating by resonance, because it has those lone pairs that it can contribute towards the ring. The bottom is just going to be donating by induction because it's just an alkyl group. It doesn't have any lone pairs or anything it can donate, resonate with. So the top group is going to be the one that wins for the directing. And so this one is going to be orthopara again. The para position is already taken by the group that we already added on. So we're just going to throw this one into the ortho position instead. And since the molecule is symmetric, it doesn't really matter which one you throw it onto. Either one is fine. So we've got our bromine that we added on, and then we've got the alkyl group that we added in the first step. Okay. Any questions? All right. Okay, we have a funny looking molecule here. We got a lot of stuff going on. So this reagent hopefully looks familiar to you. This is one of our strong oxidizers. But keep in mind for this reaction that we learned, it's slightly different. So Previously, we learned that it's going to take oxygens and it's going to turn them into ketones or carboxylic acids. In this case, in these conditions with H2SO4 and 100 degrees C or heat, it's actually going to oxidize the first carbon attached to the benzene ring. And it's only going to oxidize carbons. It could also oxidize alcohols, but it's not going to oxidize ethers. Ethers are going to be unreactive towards this reagent. But we don't have an alcohol, so. And the only exception for this is when we have a tertiary carbon, or technically this one's quaternary. But this carbon has already got 4 bonds to it, so you can't oxidize it. The carbon up here has 2 hydrogens that we can use to oxidize. This one down here doesn't have any hydrogens, so we can't react with it. So instead, we're just going to oxidize that alkyl group over on the top right. So again, the ether is going to be unreactive. The bottom is going to be unreactive. But this group is going to be turned into a carboxylic acid. Okay. And then in step 2, we have a lithium reagent. And so what this one does is it forms a dilithium salt where it just reacts with those oxygens on the molecule. But you just need to know that this one is going to turn a carboxylic acid into a ketone. And the other half of the ketone comes from the alkyl group that the lithium has added onto it. So when we react these molecules, got this. So this is going to be turned into a ketone. We have a CH2, and then we have that benzene ring on there. And again, that's just coming from the group that's attached to the lithium. Okay. All right. And for this last step, we have a triple bond. We have an alkyne. And so this one is going to be sort of like a Grignard reagent, not quite. But this one is a nucleophile because remember our ionic interactions. We've got that nucleophile there. And what this one is going to do is it's going to attack this partially positive carbonyl carbon, and it's going to attach itself on there. So we got what is this step here? Okay. All right, we've got the group that we just added on. All right, and then we've got our triple bond. So, okay. All right, good to go. And then again, the alcohol comes from the H3O plus step. That's just going to protonate the oxygen. Any questions on this one? No problem. So we're attaching it to either this carbon on the left here or this carbon on the right here. Either one is fine because of the symmetry. But the product of step 2 gives us 2 donating groups that we can use for our directing. But since the SCH2CH3 donates by resonance, it's going to be the stronger donator, so it kind of wins. So that one's going to be able to determine the direction for that. And then it's a donating group, so it's ortho-para, but the para position's already taken up by the other group. So then the only options we have left are going to be either of those ortho positions. So. Mm-hmm. Mm-hmm. Yep. Yep. It just cleaves off the rest of this chain, no matter how long it is, and it turns that carbon into a carboxylic acid? That's a good question. Okay, I'm going to go ahead and move on. If you have any more questions, we can get to them at the end. I just want to be able to get you guys out of here at a good time. Okay. All right, moving on to our fourth reaction. We have Br2 and light. So this one's a throwback to Orgo 1, like the first couple chapters. But remember, this one is going to add a bromine. And remember that it's going to add to the more substituted carbon. So like either a secondary or a tertiary. It's not going to add as quickly to a primary. So when we look at this structure that we've got, we have a benzene, it's got a bromine on it, and then we've got this alkyl chain over here. Another thing to remember, this one is just for alkanes. So we're not going to be adding this bromine onto the benzene ring. That would have to do one of the special reactions that we learned in the aromatic reactions. So instead, we're just going to add this bromine onto this carbon chain here. So it's going to add to the most stable position on that alkyl chain. And so in this case, the most stable position is going to be the benzylic position. And so this is kind of just a good thing to know for facts as well. Benzylic position is more stable than allylic, which is also next to a double bond, but not in a benzene. So yeah, you can just keep that in mind as well. Okay, so for our second reaction, this is also a throwback. So we have NaCN, and this one is going to be a strong nucleophile, and we've got an aprotic solvent. This one's going to be a SN2 reaction. So we're going to replace the bromine that we just put on, and we're going to put a CN nitrile in its place. And so in this case, I don't think you'd have to worry about stereochemistry because it's not indicated to you at the very beginning. So you wouldn't have to worry about putting it on yourself. If you really wanted to, just to be safe, you could show that it changes, but you wouldn't lose points for it in this case. Mm-hmm. Yeah, you could just write CN2. That's fine. All right. Okay, so we've got a Grignard reagent, and we've got a nitrile group. And so this one is also one of the ones that we learned recently. It's kind of funny. But this is just going to take the nitrile, and it's going to like remove the nitrogen on it. And it's going to turn this one into a ketone. So again, a little bit strange. The oxygen is going to be coming from this H3O+. I don't believe you have to know the mechanism for this one, so this one might just be kind of a memorization thing. But we've got nitrile to ketone. So we've got our structure here. So again, you don't really need to worry about stereochemistry, but if you really wanted to, just to be safe. And then the other side of the ketone is just going to come from the alkyl part that's on the Grignard reagent. So in this case, we're going to be adding CH3, CH2. All right, there you go. All right, any questions on that one? All right. Okay, this one's interesting. If I recall correctly, this one's probably pretty recent. But this dithiane, I think is what it's called. We can use this one to create aldehydes and ketones. So it's a very strange reaction, strange way to create an aldehyde or ketone, but we can do it. And so the biggest thing to remember for these ones, there probably will definitely be a question like this on your exam with this structure here. But you'll want to remember the butyl lithium. And so what this one does is it deprotonates this dithiane, and it gives us a carbanion. And so then what we can do with this carbanion is we can kind of do sort of an SN2 reaction, not really. But we can add on an alkyl group to this position to kind of do a carbon-carbon forming reaction. So in this case, it's kind of like a synthesis, so you kind of want to work backwards. Sometimes she gives it to you like this, where you kind of have to put the reagents. Sometimes she just gives you the reagents and you have to show the steps. But in this case, since we're not given the reagents, it's kind of like a synthesis question. But our end goal, we know that we form the ketone or the aldehyde. In this case, since we have a hydrogen over here on the left, if it helps, you can draw it out kind of in your beginning structures. But we want to add the alkyl group to the right side here. And so what we can do for this one, it's, again, very strange, but we can just take this whole right half of the structure and just put that as our reagent to get it added on. And so the only change that we're going to make is we're going to put a bromine where the ketone would be added on. And then we're just going to draw that structure. And that's going to be the group that we're adding on with this reagent. So we're adding this whole little fun molecule here. And then the last step for this one is just going to be our H3O+. And so that's going to, here, let me draw this out first. I'm getting ahead of myself. So when we do step 2, we have our dithione. Again, we have our hydrogen over here. And then we have the alkyl section that we just wanted to add on over here on the right. Okay, and so now when we do our H3O+, that's going to kind of cleave off the dithione right here, and then it gives us that either ketone or aldehyde. If you wanted to form a ketone, you just do another butyl lithium step, and then the alkyl halide of whatever you wanted on the left. So, any questions on that one? What's up? Oh yeah, that's right. I forgot. I knew I was missing something because I knew it couldn't be that simple. So H3O+ and HgCl2. You sure? Okay. Hg2Cl. All right. Okay. Going on to the last reactions question. Okay. So we've got our carboxylic acid. We have SOCl2. So this one is just going to turn the carboxylic acid into the acyl chloride. So step 1, you're just going to replace the OH of the carboxylic acid with a chlorine. So that's going to be your acyl chloride. All right, step 2, this is Gilman's reagent. You don't need to know the fancy names, but if it helps you remember them, then cool. And so what this one does is it also forms a ketone. And it's going to, the other half of the ketone is going to come from the alkyl group that's on there. And you're only going to add one equivalent on there. So it's a little bit weird how it has 2 in there. But you're just adding one equivalent of this alkyl group to form the ketone. All right. So we've got CH2, and then we've got a benzene. All right, and so we've got fuming H2SO4. You might also see it as, I believe, HSO3 and H2SO4. Something like this. So you could see it as fuming H2SO4 or just HSO3, H2SO4. So this one's the same reagent, but this one just adds on a SO3H. It's one of our EAS reactions. And so with EAS, again, we're going to have to look at our substituents and the donating for the positions that we're going to add on here. So on the left, the carbon that's attached to the benzene ring is going to be a carbonyl. So this one's going to be a withdrawing group. On the ring on the right, we just have a CH2, so this one is going to be a donating group. And so remember, withdrawing groups are going to deactivate the ring, so we're not going to react the left ring, we're going to react the right ring because it's activated with our donating group. And so again, for donating, ortho or para. Again, in this case, since there's nothing else on the ring, I would just go with the para position because it's the less hindered. And then we're just going to throw that SO3H group on there. Okay, and that is the final reaction. Any questions on this? What's up, Hamza? I knew it. See, we talked about this the other day. Yeah. Okay. Honestly, if you put Hg2Cl, they probably wouldn't care. They'd know what you're talking about. But yeah. Okay. I'm gonna go ahead and get moving on just so we can get out of here. If you have any questions at the end, you can always come up. So we've got our mechanism. Oh boy. So some strong contenders for this one are going to be your EAS or your NAS mechanisms. So definitely be sure to look at those just because those are probably the best bet for your mechanism. Because again, aromaticity, you know, the whole big topic of the chapters. Anyways, so we've got a strong acid here. We've got some nucleophiles. We've got some OHs. So this is kind of like a lot of the other ones that we've done so far. We're just going to take one of these lone pairs and we're going to steal that hydrogen because that's what nucleophiles like to do. So I'm just going to start off here. I'm not going to worry about the left structure right now. I'm just going to see what happens when I take this one down. All right. So when I protonate this oxygen, I form a water molecule on there. And so that's going to be a good leaving group. So this water can just head out. And then we're left with a carbocation in its place. And so looking at our end product, numbering carbons is always a good idea. So I'm just going to do that real quick. 1, 2. I'm going to try and keep it on the same like parent structure. So 1, 2, I'm going to just say 3, 4. And then this is like the other structure that we were given that I'm just not going to worry about. So we've got 1, 2, 3, 4. So right now what we have 2 methyl groups on that second carbon. On the right over here in the end, we have, if we're kind of ignoring this for now, we see that we just have 1 methyl group on there. And carbon 3 is connected to an additional methyl as well. So what I'm going to do for this is I'm actually going to do a methyl shift. So I'm going to steal one of these methyl groups and just move it over to the carbocation. So now we're left with this. So again, don't forget, when you move a methyl or a hydrogen or something like that, you're always going to have your carbocation just in a different spot. And so now this looks a little bit more like our end product. And so with this positive charge, what I can do is I can react it with another nucleophile from the left structure, because we can see in the end we want them to be joined together. And so initially you might look towards the lone pairs, but again, always just be sure to double check with your end product, kind of work through it at the same time. Do one step, look at your end product, do another step, look at your end product, just so you can kind of stay on track. So we're not joining the two together with this oxygen. The oxygen actually just stays as it is. We're actually joining these two together at this benzene ring. So what I'm going to do is I'm actually going to redraw it real quick. That's what I'm going to do. I'm actually going to take one of these double bonds, and I'm going to have that attack the positive charge. So we're just going to do that. Okay, I think I drew that right. Okay. All right, so we've added on our structures to each other. So we're going to be left with okay. So again, we haven't gotten rid of our carbocation yet. If you remember from like one of those ring shift ones where you like go from like a 4 to a 5 numbered ring or something like that. So we reacted this double bond. And so 2 is now connected to the new structure, but 1, in this case, lost a bond because it lost its connection with that double bond. So we're going to form a carbocation here. And so again, this is where your like EAS or NAS is going to come in. It's probably going to be in there somewhere. So we have a benzene ring, and now we have a carbocation in that ring. And so we're going to do the whole EAS, what is it called? The resonance going around the ring. And so this is going to be a very big part of the question. You're definitely going to want to show this because it's probably going to be like half of the points, if not more. So we're pretty much good to go on the right. We just have to worry about over here on the benzene ring on the left. So we have a couple of options that we can choose from in regards to working with that carbocation. We have a lone pair up from the oxygen that we can work with. So if we just push one of those down to satisfy that carbocation, the oxygen will now be positive. But we satisfied that carbocation, got that. So that's one of our resonance structures. Another way we could go, we could use the double bond from the benzene ring itself, and we could just move this carbocation kind of around the ring. So we've got this. I'm just going to draw this because I don't want to draw that a billion times. And then we could keep going. We can go with this double bond down at the bottom right. So we're not really getting anywhere. So you might ask yourself why you have to show this on your exam. But this is kind of what contributes to the stability of benzene. And again, the aromaticity and benzene stability is kind of like the big thing. So you'll definitely have to show this on your exam. But in any case, we can't really do anything else from here. So we've got all our resonance structures. We just have to kind of go towards the product that we're trying to form. So you can see that we basically just reform the double bond to reform the benzene. And so what we can do, I'm just going to redraw it real quick so it's a little bit neater. All right, so what we can do is throw back to the first step where we took that hydrogen, we formed a negative fluorine. So now what we can do is we can just do a simple elimination. This fluorine can take back a hydrogen, and that hydrogen can donate its bond back to the benzene ring to reform the benzene structure. And then you have your final product. Any questions on this one? Yes. Yes, 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 yes. Do it. Even if you don't know what you're doing and you like suck at resonance, try, because this is like the biggest part of this chapter. So yeah. Mhm. Whenever you do something with the benzene. So with these first steps over here, we didn't really do anything with the benzene. It was just kind of on that alkyl side chain. But once we got to this step here, where we attached the left structure to the right structure, and we formed a carbocation in the benzene ring, then you're going to do your resonance. Yeah. Any other questions on this one? Okay. All right. Again, if you have questions afterwards, you can just come up and we can work them out. Okay, synthesis. Definitely know your ortho-para meta directors, your EAS, NAS reactions. Those are going to be fair game. You can see we've got some nitro groups on there, so there's probably going to be some EAS on there somewhere. We're given benzene, we're given alcohols of 2 carbons or less, and that's it. So not too much, but that's okay. We can make it work. So when I look at these, I look and I see we've got an ether. And so ethers are great molecules for joining 2 different things together. So I'm just going to split the molecule there. So we've got our left benzene and we've got our right benzene. Okay, so we've got our nitro, got our CH2, CH2. And so in this case, what we're going to want to do to form this ether is we're going to want to work with a halide, and we're going to want to work with a nucleophile. So kind of like an SN2 reaction. The only difference is that, well, it's not really a difference, but we're going to have that oxygen be our nucleophile. It's going to be negative. So when those come together, they'll kind of do like an SN2 sort of reaction, and then they'll form that product. So from here, we can just choose whichever one we want to work back first. I'm going to do this one. And so we have a bromine on here. So we could do a bromine addition reaction, Br2 light, maybe, or we have like the HBr reactions that we did with alkenes. And in this case, we are going to do the HBr reaction because if we did Br2 and light, that would add on to the secondary carbon instead. So we don't want to do Br2 light, we're going to want to do something else. And so, if you remember this one, hopefully, what we can do is if we have an alkene, we can add our bromine on, and we can specifically force it to add on into the non-Markovnikov position, and that's how we can get our primary halide. So we've got that. And then going backwards, we've got a double bond. Easiest way, in my opinion, to make the double bond, H2SO4 and heat. So we've got our dehydration from an alcohol. All right. Okay. That one? I think you can do that, right, James? It's like the alternative pathway. Going, instead of using the H2SO4, using something else.
Yes.
I'm pretty sure PLCO3 does the tertiary carbon, doesn't it? Yeah. Okay. I will get back to that. I'm going to do it this way real quick, and then we can look at it. Oh, my bad. Is that what you're going to say? Okay. Okay. All right. Okay. So we have an alcohol on here. We have our meta group. So thinking back to the reactions that we can do to add carbons onto a benzene ring, we can do our acylation or alkylation. For the purposes of synthesis, I would always go acylation over alkylation, just because if you remember when we talked about alkylation, it kind of has some problems. It does polyalkylation and it does some weird stuff. So acylation is usually the best bet. So we're going to want to form our little ketone. This is what we're trying to get at to do our acylation product. Only problem is we have to go from this to the alcohol. So we need our reducing agent. So we have a couple of options. We have LiAlH4 and H3O plus. We have NaBH4 and ethanol. We also have, what is it called, rainy nickel. So of these reducing reagents, we also have the Clemmensen reduction. But out of these reducing reagents, we're going to want to go with NaBH4 ethanol as our best bet, just because these other reducing reagents are going to be very strong reducers. And so Clemmensen, if you'll remember, it takes it all the way to the alkane. So that would just completely get rid of our alcohol. Rainy nickel, this one, it reduces everything. So it's also going to reduce this nitro group, actually. So that's not what we want. And then again, LiAlH4, that one's also a pretty strong reducer, so it would probably also reduce the nitro group. So in this case, we're just going to go with NaBH4. It's a reducer, but it's a little bit more mild than the other options that we have. Okay, and so again, we wanted to go back to this. So we've got our little ketone. And then from here, we just have to figure out the orthopara directing stuff. In this case, both of these would be meta directors. I am just going to go back to the nitro group being on there. And then we'd have our Friedel-Crafts acylation. So AlCl3 is going to be our catalyst. And then we need our acyl chloride. So we're just going to replace the side that's attached to the benzene ring with that chloride. And so now we have our two reagents. Keep in mind that we have to start with alcohols of 2 carbons or less. So we actually cannot stick with this acyl chloride. We're going to have to work this one back as well. So I'm just going to do that one first before I forget. And so this one, it's not too difficult. We can do our SOCl2 to go back to our carboxylic acid. And then from here, we can just have our 2-carbon alcohol and use a strong oxidizer. So I'm just going to say Jones. It's the easiest to write and remember. And we're good to go on that one. We've got a 2-carbon alcohol. Then over here, all right, sorry. Okay, so we're just going to do one of our EAS reactions. We've got HNO3, H2SO4. That's going to do our nitration. And since we don't have anything else on the ring, we don't need to worry about it. We just got our benzene. And so that's going to be good to go there. So now we just have to go back to the beginning and work the other side. Love that. I'm just going to move this over. Okay. All right. So this one's a little bit funky. We've got a O minus. We got a nitro group on there. And so if you'll remember from your NAS, what we can do is we can do our NaOH, and we can use 2 equivalents of this to deprotonate the oxygen to get us our O minus. And then the previous step of that, we would have our we'd have our nitro group, and then for NAS, remember that you're replacing a halide that's on there. So I'm just going to do bromine, and then from here, we just need to get back to benzene. So we have 2 groups that are para to each other. Remember, even though bromine is a withdrawing group, it's going to be orthopara. So we're going to want to add the nitro group on second if you're thinking about it from the beginning. So we're going to want to start with our bromine on there and then add our nitro group to get that para position. And then from here, we just need to go back to benzene, and so we can do our Br2, Fe, Br3, and then we're good to go. So again, EAS, NAS, definitely know your stuff on that. It will most likely be the main part of your synthesis and your mechanism. What's up, James? For acylation?
Yeah.
Oh, so you're saying we need to do the nitro? You right. Okay. So I would probably lose a couple points, but basically what James is saying is instead, we're going to start with this, put the nitro group on there. That's the other thing I was thinking about. I knew the polyalkylation thing, but I forgot about that. Thank you. So then from here, we'd add on our nitro group, and then you'd continue with it. So same steps, you just need to make sure that the nitro group gets added on after you do the Friedel-Crafts. Okay. Any questions on this one? Okay, and I move on to our spec. Okay, all right. So remember, first step, we want to do our unsats. So we've got 2 times 11 plus 2 minus 14. So just 2 times carbon plus 2 minus hydrogens all over 2. So that's going to be 22 plus 2, 24 minus 14 over 2. 10 over 2 is going to give us 5. So again, remember, whenever you have something that's 5 or more, like 99.999%, it's going to be a benzene. A way to double check that is if you go to your proton NMR, if you have something between like 6.5-ish to like 7.5, that's going to be your benzene region. And specifically in this case, we've got our doublet signal. And so that's going to indicate that we have a para di-substituted benzene. And the reason for that is we have our hydrogens. So these 2 hydrogens are going to be equivalent, and these 2 hydrogens are going to be equivalent. So they'll stack together on the same peak, and then they split each other. So they have a doublet peak. Shorthand, just remember doublet is going to be para-substituted benzene. Okay, so then we've got our other peaks. Oh, sorry, let me go back to the IR real quick. Okay. All right, so we don't have anything in our alcohol, unfortunate. There's no alcohols in here. This region is just going to be our CH stretches. It's not going to tell us too much. But remember your 1600 to 1800-ish region for your double bonds. So carbon oxygen, carbon, 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 nitrogen, but we don't need to worry about that right now. So we do have a peak here. And so it's a very strong peak. So this is likely going to be our carbonyl peak. And we've got 2 oxygens and we've got no alcohol peak. So kind of checks out with that too. All right, so going back to our proton NMR, we have a 3H peak. So that means that the carbon that we're looking at has 3 hydrogens. This is a singlet. So this means that this carbon is not going to have any neighbors. It's either going to be connected to maybe carbonyl that doesn't have any hydrogens on it, or it's going to be next to like an oxygen, like an ether or something like that. Or it could just be connected to the benzene ring directly. Okay. Then we've got this kind of weird peak here. I'm going to skip it for now. Put all my problems aside for later. So we've got a 3 hydrogen peak here. Again, that means we've got 3 hydrogens on that carbon. Again, we have a singlet. So this one is also going to be connected to maybe a carbonyl, maybe connected to the ring itself, or connected to an oxygen. And so this one is very far downfield, de-shielded. It's in the 3.5 to 4. Normal alkyl peaks are generally in like the 1 to 3-ish range. 3 is kind of getting up there. So I'm going to say that this one in particular is going to give us our ether peak. Okay. So right now we've got a para-substituted benzene. We've got an ether. And we've got a CH3 that's connected to something. All right, going back to this peak in the middle. So we've got a 2H triplet, 2H triplet. All right, so our 2H is going to indicate that we have a CH2. We have a triplet, so that means that it's going to be adjacent to a carbon with 2 hydrogens. And so since they're so close together, these are most definitely going to be connected to each other. Again, they kind of check each other out. So if we're looking at this one, 2H with a triplet, so 2 neighbors, that checks out. If we're looking at the one on the right, 2H with 2 neighbors, that checks out. So adding to our list of pieces, we've got a CH2, CH2, and they're not going to have any neighbors on their other side because that would affect that splitting there. Okay, so now we just need to put this together. So the 2H triplet peak is also kind of far downfield, not too bad, but it isn't about like 2.8, I would say. So that's not as far as being connected to an oxygen maybe, but that would be far enough for it to be connected to the benzene ring. So I'm going to start throwing my benzene together. I'm going to say we have our CH2 connected there. On our right side, we're going to have something that is not, that doesn't have any hydrogens. So we could either do our OCH3, or we have a carbonyl carbon, remember. So we could do this. Okay. So I am going to say that over here on the left, that's not likely going to give us what we need, just because the only other carbon that we would have would be the carbonyl carbon. And that would force it to be an aldehyde. And when we look at our peaks over here on the far left, we don't have any aldehyde peaks. So aldehydes and carboxylic acids, they're going to be even further downfield than the benzene. So they'd probably be, I think aldehyde is about like 9, right? Yeah. So we've got 9 to 10 for aldehyde, and we've got like 11 to 12 for carboxylic acid, but we don't have any peaks down there. So I'm going to say that we don't have an aldehyde. So our only other option would be to use the carbonyl carbon next to the CH2. And so that gives us, what else do we have? We use this, we use our benzene, we use our carbonyl. So we have our OCH3, and then we just have our regular CH3. Okay. Okay. All right. So we have this CH that's kind of been left by itself. We said that it could be next to something that doesn't have any hydrogen. So we said it could be next to a oxygen directly, or it could be next to a carbonyl. I'm going to throw this one next to the carbonyl because it is not as far downfield as this other one over here on the left. So it's not going to be directly connected to an oxygen or anything like that, but it could be connected to this carbonyl instead. And so then that just leaves our last piece as this OCH3. So we can't connect this anywhere here because that would give us too many bonds on that CH3. But we do have this other pair spot on the benzene that we can throw it in. So that's what I'm going to do. All right. And then I like to use the carbon-13 NMR to kind of double check to make sure I have the right number of carbons. On the exam, you'll also have the sheet of values that you can use to look at. But I like to just count the number of carbons. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we've got 9 different carbons. We have 11 in our structure, but this is fine because these carbons here are going to be equivalent because of the symmetry of the ring. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different carbons. We did our proton NMR. Everything looks pretty good. So I'm going to throw this as my answer in the box. So we've got okay, and that's going to be our spec. Okay, guys, any questions on that spec question? You guys are tired? You guys want to go home? First day back. Okay. All right, well, we're done. Hamza will be here tomorrow to do the 2016 exam. Other than that, if you have any questions, come up, feel free, and have a good night. Bye, have a good one.